Hi, my name is Carolyn Jacobs and I am a lecturer at the University of Queensland. I work for the School of Mechanical and Mining Engineering and my background is mostly in aerospace engineering. My research has focused on what we call plasma. So plasma has many different types of applications and I've worked in a couple of different areas. One interesting area of application is using plasma to look at atmospheric entry. So if you've got a spacecraft that's entering an atmosphere, it comes in very fast and the gas in front of the craft gets quite excited as it gets squashed out of the way and becomes a type of plasma. And so as an engineer, I look at understanding more about that plasma and how it heats up the surface of your spacecraft. You can also look at how that plasma interacts with your heat shield materials. Another interesting area where plasma research can be quite important is biomedical research. So some of the plasmas that we've looked at have been what we call cold plasma, where you can look at something that looks like an electric discharge or a spark. And you can work with medical applications such as wound treatments for chronic wound healing or sterilization of surfaces and deactivation of bacteria.
One person has asked, what are solar eclipses and lunar eclipses? Our moon orbits the Earth about once every 29.5 days, and we see it go through a number of phases, from new moon, where it is completely dark, to the full moon, where we see a nice circular moon. This variation is due to the position of the moon, the sun, and the Earth as the moon rotates around our planet. If the moon is in between the Earth and the sun, we will see what is called a solar eclipse. From the Earth, we see only the dark side of the moon, what we know as a new moon. The sun lights up the half of the moon that we can't see, but if the moon's shadow happens to fall on the Earth, we'll see a solar eclipse where the moon covers a section of the sun. A lunar eclipse is an eclipse of the moon rather than the sun. This happens when the moon passes through the Earth's shadow. From the Earth, we see the bright side of the moon, so a lunar eclipse can only happen at full moon. Even though the moon orbits the Earth every month, we don't have eclipses every time because the angle at which the moon orbits the Earth is a little different to that at which the Earth orbits the sun. The visible light spectrum is the part of the electromagnetic spectrum that we can see with our eyes. The electromagnetic spectrum is much larger than the part we can see and is divided up into different regions. We can define these regions in different ways, but a commonly used measurement is wavelength. If you think of visible light as a rainbow from red through to violet, we say that red light is at a wavelength of around 700 nanometers and violet is around 380 nanometers, with the other colors that you would be familiar with in between. Other parts of the spectrum that you might have heard about are radio waves, microwaves, and X-rays. Radio waves and microwaves have much larger wavelengths than visible light, while X-rays are much smaller. If you get a bottle of sunscreen, this is trying to protect your skin from ultraviolet light that comes from the sun. This ultraviolet light is just a bit smaller in wavelength than visible light and goes from 200 nanometers up to the start of violet light.
To answer this question, I'm going to tell you about some of my research in atmospheric entry. To do this, I want to start with imagining that we have a spacecraft. Now, this spacecraft could have been on a mission to an asteroid to bring a sample back to Earth, or we could be sending a Mars rover into the Martian atmosphere to land and explore a little bit more about Mars. Now, whatever that atmosphere is, we're just going to think of it as a gas. Okay? And we've got a vehicle coming into that atmosphere. It's coming in so fast that our gas actually doesn't have time to get out of the way properly. And so what we see is that it's almost squashing the gas in front of the vehicle. So we start to see the formation of what we call a shock layer, where you have an initial bow shock, where you see a sharp jump in temperature and pressure, okay, and then it might ease off a little bit. And then we also have right up against the wall of our vehicle what we call a boundary layer, where there might be some other variations in temperature because of that boundary layer on our surface. What we're interested in is learning more about that gas, or plasma, if you want to call it a plasma, okay? Because generally it's excited enough that we're seeing ionization and other reactions where we actually end up with a plasma. If we can learn more about that gas, we can learn more about how it's going to heat our vehicle. Okay? We can also learn more about how that gas is going to interact with our heat shield, because maybe our heat shield is going to interact with the gas and we're going to see some different reactions at the surface. Where light comes into it is that we use a technique called emission spectroscopy, where we break up the light that gets emitted by our excited gas, and we look at the different wavelengths. And so the information we can get from this light could be what our atmosphere is made up of. We can learn more about what is actually there in the atmosphere. We can look at what is the temperature in that shock region or that excited region in front of our vehicle. We can also use spectroscopy and the information from this to actually look at testing heat shield materials, and we can put samples in and actually simulate re-entry. And we can look at learning more about how hot the surface of our heat shield is likely to get. What we're wanting to do, okay, is then take this and apply it to actual spacecraft that we are designing for future missions. One major benefit of understanding more about the heating of that vehicle and how our gas can affect the heating is that it's going to let us potentially be more efficient about how we design our heat shields. Okay? You've got to remember that it's very expensive to send vehicles into space and to do all these experiments. Okay? But we need to make sure we've got enough protection so that when our vehicle enters the atmosphere, it doesn't run into difficulty, and we protect our experiments or we protect our astronauts. So if we can make our design of these heat shields more efficient, then it means that we can save money because we're saving weight. It also means that maybe we can send more experiments or different types of experiments. Okay? And so we can learn more in the same mission.